Gentlemen, so continuing our series on the workings of the universe and how it is powered by light, there are some other things that we need to consider. For example, we have a lot of effects that we know light can achieve. I mean, you look at what a laser can do in terms of heat, and it's a lot. Focused light can do incredible things. And I don't know if you knew this, but how lasers work is photons bounce back and forth. Not so much, but yes, we do use photons in the process, and here's how this works. We take a ruby rod, for example, and it's usually a gem laser. All our earliest lasers were based on gems, and here's why. Here's how the physics of lasers work. I did say I studied photonics. I wasn't kidding. I earned that honorary degree. And so how this works is we take a ruby rod, mirror one end, lightly mirror the other end, heavily mirror the back end. Just slightly less, we mirror the front end. These bounce back and forth, but it's not the photons. It's the individual molecules that comprise the ruby. That's why we call it a ruby laser or a sapphire laser or whatever kind of laser it is. Or a chemical laser if it's chemicals. Because we excite the molecules of that, carry them on a beam of light, and that is a laser. That is why the laser takes on the color of the object being fired. I don't know if you knew this, but when I invented 3D printing, it's actually laser based, and the concept was to build things molecule by molecule using lasers. Only it's such a hugely expensive production process and hugely energy expensive that, well, it's not really practical for mass production. But it does allow, and the theory allows, for us to manufacture things with molecular perfection. But it would take you 2 years to build a car. So, there's that. And the expensive nature of that means you're burning out gems in the lasers all the time. And you would be burning rubies and sapphires and emeralds and all kinds of shit while you use these different lasers. And so you really wouldn't want that because it's very expensive. Then we came up with the ability to artificially create these gems. You may wonder what drove that market. That is where the artificial gem market has actually come from, is because the laser industry using gems has been so expensive and we're destroying these gems. They do not come back the same because we are using their molecules. We are exciting their molecules and ejecting their own molecules from them using photons. And how that works is we hit it with bright light and it excites the molecules inside and they start back and forth bouncing with the photons. And those beams of photons bounce back and forth between the mirrors, gaining speed and energy with each bounce. Bup, 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 bup. No, the photons are always traveling light, but it's exciting the molecules. And those molecules start to travel faster and faster because unlike other molecules, the ruby molecules aren't traveling light speed all the time. That's light, baby. And this is where we get to a laser. So now you get the light molecules bouncing back and forth, exciting and picking up all of these other molecules and making them go increasingly faster and faster and faster and faster and more energy until they're bouncing back and forth so fast that they break through. We can control how powerful the laser is by how powerful the mirroring is and how long they stay in the cycle and how powerful that whole setup is. On top of that, they have to be cooled, which means we needed liquid nitrogen and all this stuff. Long story short, that is the essence of how a laser works. And so it is entirely theoretically possible that our sun is, through internal processes that we don't really understand, making these types of things happen within its core. I mean, we do have molten gem material in the core of a planet. We know that. But what we don't understand is whether or not the sun has any of those materials, and if so, how that's working. What if the sun's core is made of a lot of light reflective materials? Maybe gemstone type materials in a molten state. We really don't know. And so until we know, we don't really know what to expect from the reflective properties of the gases involved. We need to do a lot more detailed studying of our sun, as always, and the light that comes from it as a result can vary greatly, as I've shown, and as science has shown. And so in this one, I wanted to cover a couple of the reasons why this kind of stuff matters. For one, when we're talking about, as I talked about before, precision outgassing, that makes a difference. But it also makes a difference to other things. And I wanted to talk about, for example, how our magnetic sphere might have developed, because we can take an electromagnet, and no matter how powerful we make it, it doesn't have a magnetosphere the way our sun does. And our core doesn't seem to be magnetic enough to account for how powerful our magnetosphere really is. But imagine that the sun is created by its core, by the molten shit the sun spews out when it does a massive CME. And that would mean that then hardens a crust and starts to form. Well, that's the best we can figure out of how that happens. But we also know that same process can do things like produce water, like we see on this planet. It can produce incredible things. We know that. There are very exciting things happening in planets and in our sun. And given that these things all come from the sun, we have to assume that these things are capable in the sun. Now, what if the sun is producing water and then that water is being vaporized in locations, and the light passing through that, depending on the chemical qualities, might very well form something of a chemical laser. And we might see very strong beams. Now, I'm not saying they're laser strong, but we could see short bursts that are from our sun. And I think that's something we haven't accounted for, is the variation in density of particle beams and all that, and the energetic nature of those beams, and how much energy is really being carried and how fast they're really traveling. We really don't know. We haven't put the framework in place to observe those things at that detail and see. And we need to put together a new package for a new satellite, guys, and put that into orbit around the sun. So I don't have to tell them what kind of packages need to be installed. They'll do that quite handily on their own. NASA's pretty cool like that. But I do want to lay out the framework and how I think that this is starting. So imagine for a minute that the sun has spit out some electromagnetic material, which we know it has in it, just like our core does. Lodestone, all kinds of things are magnetic in our core. And so it's also getting charged particles from the sun. And that's the thing. I think our magnetosphere actually starts very weak and is bombarded regularly by the energy from the sun, and it's electrically charging that magnetosphere. It's supercharging it all the time. And we're looking at the reason it's so strong is that we're looking at 35 billion years of our sun strengthening. Because the sun is getting close to the end of its life cycle, we're seeing as strong as it could be kind of thing. Because once the sun starts to transition out of this life cycle, its energy starts to fade and it gets weaker. So a sun is only really erratic and spitting out huge amounts of energy twice in its life, once at the beginning and once at the end. And so it is increasingly energetic nowadays and spitting out more and more particles, which is a bit of a problem in itself. Maybe not. We really don't understand enough to know. And that's the thing. We know that our atmosphere and magnetosphere are protecting us from a lot of the charged particles that we see. We know that solar panels are a lot more effective in space when they're closer to the sun and there's no atmosphere in the way. But that partly has to do with the way light refracts. And this is something else I wanted you guys to consider. The light we see through our atmosphere has traveled through our atmosphere and our magnetosphere, which means we should exhibit less charge in those particles than they would in raw space, theoretically, because as they pass through our magnetosphere, it should pull away some of the energy, and so we should see a lesser charge on the particles as observed on Earth. And since all of our measurements on the energy those particles carry is what we see based on Earth, we really need to look at the energy amounts in particles traveling through space to see if that's right. And the best thing to do is to, again, put a satellite around in orbit around our sun to see all these things. And so now that I've covered that part, I do want to cover a couple of the things that basically suggest that, well, this all makes a lot of sense. And it explains why different planets can be ejected at different levels, and why the bigger planets, nobody's ever been able to explain this, guys, why the biggest planets are the farthest out. Well, allow me to explain. So let's say the sun spits out a supermassive chunk of itself, and at one time the sun was much, much bigger than it is now, maybe double the size, maybe 10 times. And as it expanded and contracted, which we know they do early on in their life, it spits out and leaves behind both, because on some levels, as it's contracting, it's leaving behind some of itself, but it's also spitting out huge chunks of itself. We call them CMEs, coronal mass ejections. And we don't call it a mass ejection for nothing. It's emitting mass amounts of itself and spitting it out into the universe. Well, it's not that that doesn't account for anything. These things go out and they cool. And when it's just plasma, well, that's all right. But some of these are basically volcanic discharges too. You have to look at it that way. The CME comes in a lot of ways. A coronal mass ejection can be just energy and light, essentially, and radiation, or it can be a physical mass of 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 stuff that's coming rushing out of the sun. And so all of those things matter to how this works. So assuming that's the case, which is pretty much the current model and the best we can figure, the best I could figure, when that happens, the smaller an object is, the shorter the distance it would be thrown by the rules of physics, because an object that has more momentum will travel farther. And their pull would have to be stronger. The charge they're getting from the sun would have to be stronger to be held in place. And so I think that the small planets, having a smaller surface volume, need less particles to charge them sufficiently to stay in place. And because they had less mass when they were ejected with less energy. And so they didn't travel as far out. And so we can see how the planets would align and why they get seemingly bigger as we go out rather than smaller, which is what gravity would suggest. Well, if my theory about light is correct, this explains everything. I did say early on it pretty much explains everything. And this is what I was talking about. It just, the more I think about it, the more it explains all the little details that we see, or at least it presents a possible explanation that is from the same unified source, which by definition makes it a unified theory because it's explaining all these things in a unified way, which is exactly what Einstein predicted would be possible. Looks like you might have been right on that one, because it is very much that way now that I have this and looking at all the details. It absolutely works in every way. And so at this point, I pretty much feel like that's good enough. I've explained everything. I've shown how this could work. I've explained the physics as how this could work. And then the rest is really up to NASA, of course, and the scientists to see how much of this really is happening and describe it in their own terms mathematically and verify everything scientifically. That'll take time. I don't expect it to be, anytime soon before we really know the details. If I were you, I would expect between 10 and 20 years we'll have the framework in place to detect everything we need to, and we'll have enough data set that we'll have all the answers. But at least if they were to take my theory seriously and start looking into all these things right now to see how they all fit together, I mean, my guess is there already are. Tesla, a lot of other people have studied these aspects, and you need to not just start from scratch, but look at the volume of work already that's been done and the science that's been done on this, and to show, because I know that at some points people have suggested that the universe may act like a charged circuit, and nobody could understand how. And I wanted to explain that a little bit. I talked about pushing electrons in the last video. Now consider that the sun gets to a point where it's now charged the solar system when it's very young. And at this point, that all starts to make sense because these objects are being held in place by their magnetism, which is only reinforced over time. Now, you would think these objects would get closer, but they're so massive that it would take a huge amount of electromagnetism to make them come with force. And they're not doing that. They are at their limit, kind of thing, of how close they're going to get. And their motion, naturally, when two magnets come together, doesn't lead them to do this. Even when they're of the same pole, it leads them to do this and come together in a rotating way. And I have done experiments with that. You can see those. They're up on the channel, and they'll show you how that works, magnetically speaking. And so I feel like I've covered all the bases on this channel over time. And if you really wanted to know how the universe worked, I go into all the details here in a real engineering way, where you get to understand all the fundamental principles without all the technical babble or education involved. But I did grow up studying all this stuff, and I was fascinated by light, and lasers, and all this stuff. I even built my own laser, and then it worked better than the original because I improved the original design, which wasn't hard. He failed to add a cooling system, and it exploded on it. My stepfather said, if you can figure out what he did wrong, you can build it. He thought it would take me a long time. No, as soon as he laid the blueprints in front of me, I told him right away. I was like, well, They didn't install a cooling system. I hope he survived. And my stepfather was stunned because there's this 13-year-old, and that was what I told him. And he says, "Okay, son, clearly you know the math." And she's like, "Yeah." My mom's like, "Yeah, that's why I told you he'd be interested. He's already read a book studying the physics on this stuff, and he actually understands it." And he's like, "Oh." And I'm like, "I've already done the math, and da-da-da-da. We'll need a cooling system when it'll need this much volume of super cooled material." And we'll need this much piping, and we'll need this, and we'll need that. And I laid out the whole design for the cooling system, built and installed the cooling system when we built the laser, and then we tested it, and it worked flawlessly, and stayed cool enough that it didn't explode on us. We built it safely, but we only did that through proper understanding. And if we'd have been the first ones to build that laser, we might not necessarily have accounted, just like he didn't, for the sheer amount of heat that gets generated by all those moving molecules back and forth in that laser. Now that brings me to another point. Now see, when light charges these objects, consider that these particles are moving back and forth in much the same way. And without knowing the internal composition of those, some things we know get very energetic and explode when exposed to enough light. Because what if in this there is a gem that's got one face showing, which is common, and the rest of it's buried in rock? Only it's not a shiny face, it's just rough, right? What if it's broken? Well, then it's like a shiny face, right? And the light hits that, and the object's light reflects in and starts bouncing around inside of there. Now, if that light were strong enough, or the radiation burst and with it was strong enough, and those particles hit that and start bouncing around inside, the chain reaction could result in an explosive decompression kind of situation where it's because some crystal inside blows out, or which could explain some of the explosive outgassing scenarios that you see. And I wanted to cover that too, because particle physics covers a lot of things, and I did say I grew up studying it. I wasn't kidding. And so I do see that particle physics can explain a lot of the things that we see, along with my knowledge of what comes from our sun. And between the two of those, I know that those effects can create all kinds of things, because you can create a laser, but you could also create explosions. We could see focus beams of light coming out of these from the same thing, our sun, hitting them with charged particles that are stronger than what we see here on Earth. Keep that in mind. Meaning you could potentially make a stronger laser in space than you could on Earth. There's a lot of things that come along here. And so we did notice too that lasers in space travel farther than lasers on Earth, and nobody knew why. I think I know why. And so I'm going to end this one. It's already getting close to 20 minutes, you guys, but I really wanted to cover some more details, because the universe is a complex place. And if we really want to understand all the details, the more we understand, the better it is.